Hello, this is Miss Moore, and today during chemistry we're going to discuss acids, bases, and salts. Today's essential question: how is the pH of a salt determined? For today's lecture, I suggest you have your calculators handy. Let's start our discussion with salts. So, a salt is just another name for an ionic compound. Fancy sciencey term for ionic compound. When a salt is dissolved in water, one of three things can happen. First, when you dissolve a salt in water, it can simply break up into its ions, which then move about independently. So for example, if we took table salt, NaCl, and mixed it with water, we would end up with pretty much a forward reaction of sodium ions and chlorine ions and still water. So basically all that happens when this salt dissolves is that you end up with two ions floating in water. Okay, another thing that can happen when a salt is dissolved in water is that the cation can interact with water, producing an acidic solution. A third possibility when salt is dissolved in water is that the anion can interact with water, producing a basic solution. All right, now we need to talk about something called salt hydrolysis. So, salt hydrolysis is the reaction of a salt with water generating H plus or OH minus ions, which leads to a change in pH. So, when we're talking about the hydrolysis of water, we are talking about points B and C here, where the anion or the cation actually interact with the water, producing hydronium and hydroxide ions. When we're talking about a salt dissolving in water, it's not actually reacting with water, and this is where you end up with just independent ions moving about. Okay, so again, salt hydrolysis is the reaction of a salt with water generating hydronium or hydroxide ions, which is then going to lead to an increase or decrease in pH, an acidic or basic solution. And being that I use the term hydronium, remember that this H plus actually interacts with the water, producing H3O plus, which is hydronium. All right. So which salts just produce neutral solutions, meaning don't react with the water, just dissolve in the water? So salts made up of group 1 or 2 cations and anions from strong acids, gave you the list there, will likely form a neutral solution when dissolved in water. So these are the guys that are likely to just simply dissolve in water. So why those? Well, let's talk about acids and bases. So strong acids produce a weak conjugate base or anions not strongly attracted to the H1 plus. So for example, if we were to take hydrochloric acid, HCl, and drop it into water, I guess I should drop this into water, we end up with an almost one-way forward reaction with just hydronium ions and chlorine ions. And this chlorine is a very weak conjugate base. It doesn't really want to hook back up with the water, hook back up with the hydrogen, producing HCl again. So this is a strong acid here, producing a very, very weak conjugate base. So the reaction is very, very forward. Strong bases produce weak conjugate acids that do not produce an H+. So for example, if we had NaOH, which is a strong base, when it breaks apart in water, we end up with Na plus and OH minus and still water. Again, a very one-way reaction, with the sodium being a very weak conjugate base. Conjugate acid. And it's So it's very much a one-way reaction. So now, if we can talk about a salt that is made up of some of the cation and anion from the previous two examples, we can see why it basically just breaks apart in water. So if we take NaCl, which we've already gone over, in water, it basically just dissolves in water, because sodium isn't going to be losing an H, so it's a weak conjugate base, and chlorine is not likely, no, I said that wrong, sorry. Sodium is not likely to lose an H, so it's a weak conjugate acid, and chlorine is not likely to gain an H, making it a weak conjugate base. This is why salts made up of a cation from a strong base and an anion from a strong acid are very likely to form a neutral solution. So basically, cations from groups 1 and 2 and any anions from strong acids, if you have a salt made up of those two things, they're likely to just dissolve in water, producing a neutral solution. All right, is it acidic or basic? So can we predict if we have a salt, can we predict if it'll be acidic, basic, or neutral when it's dissolved in water? So if a salt contains an anion that reacts with water to produce hydroxide ions, and a cation that does not react with water, we expect the pH to be basic. So if the cation does not react with water, it's going to be usually one from groups 1A and 2A, or groups 1 and 2. Okay, sodium and magnesium, calcium, all of those guys. If the salt contains a cation that reacts with water, to create hydronium ions, and an anion that does not react with water, we expect the pH to be acidic. So for point 2, the combination would be a cation from, wow, I don't know how to spell, from a weak base, and the anion from a strong acid. Because this one would react with water, this one would not. And up above, if we make it a little bit more clear, or same pattern here, this would be a cation from a strong base, meaning it won't react with water, and an anion from a weak acid, meaning it will react with water. If the salt contains an anion and a cation, both capable of reacting with water, both hydroxide and hydronium ions are produced, and whether the solution is basic, neutral, or acidic depends on the relative abilities of the anion to react with water. And in this case, we would actually have to do some math. So here we would actually have to do some math to figure it out. If we're in this scenario, these two scenarios here, we can just make a basic prediction. So let's try that. Let's try to do some predictions next. Okay, so let's take the salt NH4Cl and mix it with water and discuss what could happen. All right, let's go ahead and break apart the ions. So we're going to have NH4, 1 plus, and Cl, 1 minus, and we've still got the H2O. All right, let's think of this Cl as being a conjugate base of some acid. And so the acid that it came from would be H2, well, not H2O. Try that again. It would be from HCl, right? Which means this was a strong acid, which makes this a weak conjugate base, not highly attracted to hydrogen. So he is not going to hook up with another hydrogen. So what about the NH4? Well, NH4 could have come from the base NH3, which is a weak base, making this a strong conjugate acid. It's likely to lose that H, producing H3O, which would then make our pH would decrease, making it acidic. All right, let's try another one. We are going to work with the salt barium acetate. And we'll dissolve this guy in water, giving us the ions barium 2+ and acetate 1- and water. So question is, are these ions going to interact with the water or just say dissolved in the water? All right, let's start with the cation barium. He could have come from the base BaOH2, which is a strong base, meaning barium would be a weak conjugate acid, meaning it's not going to give off hydrogen, meaning barium's just going to stay dissolved in the water. Okay, what about the acetate? The acetate could have come from the acid HCH3COO, and this is a weak acid, which makes the acetate a strong conjugate base, meaning it is very likely to accept another H from the water, giving us OH-. And remember, Kw equals the concentration of OH times the concentration of H plus, or H3O. So if we have more OHs, that means we're going to have less H pluses, which means our pH is going to increase, giving us a basic solution. All right, let's try one more. Let's work with the salt potassium nitrate. We'll mix this guy with water. We end up with a potassium ion and a nitrate ion and still water. So what's going to happen to these ions? We'll start with potassium. Potassium could have come from the base KOH, and that, because it's one of the group 1 cations connected with an OH, is a strong base. Strong bases mean that the potassium is going to be a weak conjugate acid, meaning it's not going to be releasing an H backwards, which means he's just going to stay dissolved in water. What about the nitrate ion? Well, nitrate could have come from the acid HNO3, which is one of our strong acids, which means that NO3 is a weak conjugate base, not likely to accept an H from the water, meaning just going to stay dissolved, meaning no change in pH. So this salt is going to lead to a neutral solution. All right, on to calculating the pH of a salt solution. So our practice problem will be calculate the pH of 3 molar NaF solution. And we have the Ka value. All right, so we're going to do what we were just doing. We're going to take our sodium fluoride solution, mix it with water. That's going to give us Na and, Na 1 plus and F 1 minus, and we're still going to have water left. Let's see. Sodium could have come from NaOH, which is a strong base, making the sodium a weak conjugate acid, meaning he's just going to stay dissolved. Fluorine could have come from HF, which is a weak acid, making this a strong conjugate base, meaning he could indeed change the pH. So what we're going to be working with here then is simply the F ion and water. So we're going to have F1 minus in water. And I guess I should put in the states. This is obviously going to be aqueous. Water is liquid. And that's going to give us the acid HF, aqueous, and some OH, 1 minus ions, which are also aqueous. So now we can just use our Rice table and figure out the pH. So we know our reaction is F1 minus. We can ignore the H2O because it's liquid. We have HF and we have OH 1 minus. All right, next is concentration. Well, we started with 3 molar of NaF, which means we have, when the ions break apart, we have 3 molar of Na and 3 molar of F. So we have 3 molar of F. We don't know how much HF, or actually we do know. We don't have any at the moment, and we have no OHs. All right, so next is the change. We know that the F is going to decrease by some X. The HF is going to increase by the same X as is the OH. So then at equilibrium, the F concentration will be 3.0 minus X. The HF concentration will be 0 plus X or just X, and the OH concentration will be 0 plus X or just X. Okay, so we were given the Ka value, but being that we're looking for OH, that means we're going to need the Kb value. So we know that Kw equals Ka times Kb. So to figure out Kb would then equal Kw over Ka. So Kb equals 1.0 times 10 to the negative 14th over our Ka value, which is 7.2 times 10 to the negative fourth. So calculating for Kb, we end up with 1.4 times 10 to the negative 11th. All right, so now we know that Kb equals the concentration of HF times the concentration of OH divided by the concentration of F, all at equilibrium. So that gives us 1.4 times 10 to the negative 11 equals the concentration of HF, which is X, and the concentration of OH, which is also X, so it gives us X squared over 3.0 minus X. We can assume for now, although we do need to check, that this X is so very small that it can be ignored. So we'll ignore that. So now let's solve for X. So we can have X squared equals 4.2 times 10 to the negative 11th. And if we square root both sides, we get 6.5 times 10 to the negative 6th. So X equals 6.5 times 10 to the negative 6. And let's erase some of this stuff, give us a little bit more room. So we have X equals 6.5 times 10 to the negative 6th. To check that our assumption was valid, we need to divide our X by our initial concentration and make sure it's less than 5%, and it is. So now that we know X, we also know the concentration of OH, and we can, knowing the concentration of OH, calculate POH. So remember that POH equals negative log of the concentration of OH. So our POH equals 5.19. And the question asked us for pH, but we know that pH plus POH equals 14, which means our pH equals 8.81, which means we have a basic solution. And that's it for today. Have a good one.